Welcome to Topcast and episode 256 about David Deutsch's The Fabric of Reality. This is chapter 13, titled The Four Strands, and part 2 of my commentary on this chapter. In part 1 of chapter 13 that I went through, David outlined some of the differences in approach between Karl Popper and Thomas Kuhn and their accounts of how science proceeds, and even what science actually is. That part 1 was the theoretical backdrop for what is to come in part 2 and presumably part 3 and maybe a part 4, because today we're going to begin the application of those ideas. After all, if Kuhn is correct about how social forces in large part dictate the adoption of scientific theories, and that they can even prevent their capacity to take hold in the academy and ultimately wider society, then as an account of science generally, we should see that, say, in physics, computation, and mathematics, for example, we should see that social factors are the main determinant in how theories arise and are either adopted or rejected. So today we're going to begin with that analysis by David. We're going to compare and contrast the Popperian and Kuhnian accounts of science by applying them to a real-world example. And, of course, David, quite rightly, is going to begin here not merely with just physics in general, but with his personal expert knowledge of this area and of the history, in particular, of quantum theory. If Popper is right about epistemology and the philosophy of science, then what should happen in science is that when a theory is conjectured, then rational means are used to evaluate it by error correcting. People will criticize, and on the basis of the success or not of those criticisms, theories are adopted or not by the relevant experts or the entire field itself. But if Thomas Kuhn is right, what we will see is generally irrationality. We should see appeals to authority ruling the day, and experts retreating into themselves and holding their ideas immune from criticism as a rule, and as a means by which science actually changes over time. Again, I've got to emphasize, as I did at the end of the last episode, no one, certainly no Popperian that I've met, argues that scientists cannot possibly be stubborn and emotional at times. They're not some special species of human who always and only ever act like rational calculators of sorts. This can be considered, all of that can be considered well within the account that Popper gives. Popper's never denied that emotion and social forces play a role in the enterprise of doing science. What he does argue instead, however, is that they do not in any ultimate sense, or in even any crucial sense, determine the conclusions reached in a scientific field. Let's take some quotes. In The Logic of Scientific Discovery, he writes, quote, "There is no such thing as a logical method of having new ideas. Discovery contains an irrational element, or a creative intuition." And then he goes on to say, "The beliefs of the scientist, his metaphysical faith, his psychological makeup, or his social environment may influence his work, but they do not determine the logical status of his theories." End quote. So, a scientist's social environment may influence his work, what he does and how he approaches it, for example, and how much time he might have to spend dealing with critics, or in modern parlance, perhaps trolls. But whether the work he does is true, or, as we would say today, the best explanation or not, is not determined by social factors. It is determined by the rational process of argument and evidence. So it is strange in the modern day at times to hear actual scientists themselves sometimes argue that the reason their own favoured theory is not regarded as the prevailing theory of everything, or of consciousness, or of neo-Darwinism, and on and on and on. Sometimes they argue, especially the scientists that appear on social media from time to time, they're all arguing that the reason their pet theory hasn't been adopted is because of social factors. They're Kuhnian, at least implicitly. They are arguing that in their case, science operates according to social factors, and it's social factors that's determining what is accepted as true or false, or indeed what is true or false. Imagine seriously thinking that about science and then being a scientist anyway and continuing to do science. If it really was that hopeless, give up, go do something else, fly a plane. Or, as we'll come to, perhaps planes only fly because of social factors too. Anyway, Popper actually makes this point about science in the Open Society, of all places. He writes in the Open Society, quote, "The objectivity of science is not a matter of the individual scientist's impartiality, but of the social institution of mutual criticism." End quote. That's from the Open Society and Its Enemies, Volume 2. So there is an institution operating in science, the institution or tradition of criticism. Everyone criticizes everyone else's ideas. Nothing's off the table. That's what goes on. And basically, if you can't stand the heat in science, get out of the kitchen. Stop doing it. If you're going to retreat into, well, there exists a conspiracy, there are political forces out there in the scientific community that are preventing progress, well, you can argue that, but it's not the reason in any ultimate sense why better ideas have not yet prevailed. It is rather that they've not been thought yet and then tested and able to refute the existing ideas. People want to make progress. As Popper goes on to say, quote, "What we call scientific objectivity is not a product of individual scientists' impartiality, but of the critical tradition, which forces them to correct one another." End quote. So in other words, scientists can be biased and they can be emotional, unreasonable, and even appeal to authority at times. That can happen, but it becomes irrelevant precisely because to do science requires the application of criticism. And so what we end up having is that scientific explanations rise above all of that social stuff. People or other scientists can carp and complain and be resistant to new ideas. But the best explanation is the best explanation regardless of all that. Popper said something similar to this in The Logic of Scientific Discovery, his first book, but he was making a slightly different point. Anyway, he writes there that, quote, "Science does not rest upon rock-bottom certainties. The bold structure of its theories rises, as it were, above a swamp," end quote. I love that. There he's refuting actually foundationalism, or the idea that we derive scientific theories from first principles or axioms or certainties and so on. He's speaking about the nature of scientific theories as conjectural knowledge, rather than derivations like mathematical theorems. But this idea that the bold structure of scientific theories rises above a swamp is a good one. And the swamp can be, well, the various errors made and the false or faulty or worse conjectures. But it can also be the swamp of social pressure that Thomas Kuhn, elevates to the very top of the enterprise. Okay, so let's get into the reading for today from The Fabric of Reality as David applies all of the theory about Popper and Kuhn to the specific case of quantum theory. David writes, quote, "According to the Copenhagen interpretation, the equations of quantum theory only apply to unobserved aspects of physical reality. At moments of observation, a different type of process takes over, involving a direct interaction between human consciousness and subatomic physics. One particular state of consciousness becomes real, the rest were only possibilities. The Copenhagen interpretation specified this alleged process only in outline. A fuller description was deemed to be a task for the future, or perhaps to be forever beyond human comprehension. As for the unobserved events that interpolated between conscious observers, one was not permitted to ask about them." End quote. So there we can see this invocation of human consciousness into quantum theory, which has led to all sorts of mysticism, nonsense, and pseudoscience ever since. Only today I was listening to a particular conservative Christian commentator talking about politics and actually invoking this. But this is common across religions. This particular conservative commentator was kind of unique in my mind because he was talking about Jesus and the Christian God, and speaking about how we as human beings are able to change reality by observing it, because this is what quantum theory tells us, and in some way this justifies belief in God because God is acting through us via this method of observation that's there in the laws of physics. Okay, so I've heard this kind of thing before, but usually it comes from Buddhists and Hindus and other kinds of people. I don't often hear it from Christians. Christians don't normally need to rely upon quantum physics to back up their belief in miracles and so on. Anyway, putting that aside, there's quite a bit there in what David just wrote. Firstly, with respect to the Copenhagen interpretation, that's kind of, it was Bohr and Heisenberg, although I'm not completely clear on the entire history of this. In any case, the idea, as David says there, is that the equations of quantum theory were supposed to apply only to the unobserved parts of reality. During observation, some different physics took over. The laws of physics changed from the quantum physical laws, which they presumed couldn't possibly be the story, or at least the whole story when it comes to explaining what was going on in particular experiments. Hence, they invoked consciousness to account for what went on during observation when things appeared to change, namely, things appeared to collapse, or at least there was only one observer rather than multiple observers. Consciousness accounted for observational effects, supposedly. And those observational effects were most important or significant when measurements were made. Measurement, observation being the same sort of thing here. This is the so-called measurement problem, which you still hear about today. People will still bring up, even when you try and explain Everettian quantum theory to them, they say, but it doesn't solve the measurement problem. Of course, that's precisely what it does do, but everyone holds this aloft. The layperson with a general interest in quantum theory will read about the measurement problem, and in popular accounts, it's still regarded as being unsolved. Because why? Because they're relying upon the Copenhagen interpretation. In any case, this so-called measurement problem disappears if one simply accepts the Everettian relative state formulation of quantum theory, where the laws of physics are just universal. They apply equally to what is measured, who measures it, and the measuring devices, before, during, and after measurement takes place. And what you get out of that are a multiplicity of measurement results that really do exist. In other words, reality is multivariate, and therefore the same observer can observe different things. And when they do, this is known as differentiation. And when that happens, the observer ceases to be the observer and becomes the observers after fungibility is broken. Now, fungibility is a term from the beginning of infinity to try and explain how it is that a single object can have many identical copies, all existing in the same place and time. Read The Beginning of Infinity or have a look at my multiverse series for more on that. What is also nice in the passage that we just read is where David said, quote, "The Copenhagen interpretation specified this alleged process only in outline. A fuller description was deemed to be a task for the future, or perhaps to be forever beyond human comprehension," end quote. Yeah, so back in 1997, David wrote about that. And he wrote that, no doubt, because he'd heard such things. And now when I argue in 2025, 2026, and I can only guess for years to come yet, when I argue that we human beings are people, which are universal explainers, what is generally the first or second thing to come up in any attempt to refute me on this idea that we are universal explainers? Well, it's quantum theory, of course. This is what Richard Dawkins always holds up. Always quantum theory. It's always quantum theory that is held aloft as being the thing that will forever be beyond our comprehension, because there are certain things we just can't understand on their account. If I manage to persuade my interlocutor that in fact it is comprehensible, quantum theory is eminently able to be understood and by anyone who spends sufficient time investigating it, then almost everyone that I've ever spoken to about this or debated this will leap to what comes next? Consciousness. And you hear this all the time, especially in the various rationalist communities who perhaps disagree with parts of David Deutsch's worldview. No one can explain consciousness, they say. And so the argument goes, therefore, we are not universal explainers. Just because it can't be done now, we can't have an explanation now, doesn't mean it will forever lie beyond our understanding. That's the whole point of science, problem solving, reason and rationality, period. Let's go on. David writes, quote, "How physicists, even during what was the heyday of positivism and instrumentalism, could accept such an insubstantial construction as the orthodox version of a fundamental theory is a question for historians. We need not concern ourselves here with the arcane details of the Copenhagen interpretation, because its motivation was essentially to avoid the conclusion that reality is multivariate, and for that alone, it is incompatible with any genuine explanation of quantum phenomena." Some 20 years later, Hugh Everett, then a Princeton graduate student, working under the eminent physicist John Archibald Wheeler, first set out the many universes implications of quantum theory. Wheeler did not accept them. He was, and still is, I should pause there and quote, was. He passed away in 2008. The great John Archibald Wheeler. Rest in peace. Anyways, let's keep going. Wheeler did not accept them. He was convinced that Bohr's vision, though incomplete, was the basis of the correct explanation. But did he therefore behave as the Kuhnian stereotype would lead us to expect? Did he try to suppress his students' heretical ideas? On the contrary, Wheeler was afraid that Everett's ideas might not be sufficiently appreciated. So he himself wrote a short paper to accompany the one that Everett published, and they appeared on consecutive pages of the journal Reviews of Modern Physics. Wheeler's paper explained and defended Everett so effectively that many readers assumed that they were jointly responsible for the content. Consequently, the multiverse theory was mistakenly known as the Everett-Wheeler theory for many years afterwards, much to Wheeler's chagrin, end quote. So that's an amazing fact. Wheeler disagreed with Everett's theory of the multiverse, but the theory for a little while was known as the Everett-Wheeler theory. Anyway, so although Wheeler could be considered an opponent of the relative state formulation, or Everettian quantum theory, he wrote a clarifying paper, and one might well say a praiseworthy accompanying explainer of sorts to Everett's paper in the Reviews of Modern Physics. And well, here it is. We can read parts of this. Let's see what Wheeler writes here. I won't go through Everett's paper. You can easily download that yourself. Okay, that was the original first paper that presented Everettian quantum theory, the relative state formulation of quantum theory. But here's Wheeler's assessment of Everett's relative state formulation of quantum theory by John A. Wheeler. I'm not going to read the entire thing, but a few passages will give the flavor of what he's doing here. He begins with, quote, this is from Wheeler, "The preceding paper puts the principles of quantum mechanics in a new form. Observations are treated as a special case of normal interactions that occur within a system, not as a new and different kind of process that takes place from without," end quote. So he's there saying that what Everett is doing is rejecting the Copenhagen interpretation. There's no special physics for observation. They're just normal interactions, skipping a very substantial part of the paper. And I'll go to the bit where the Wheeler writes, because, okay, just keep in mind that the entire problem, in a sense, with what physicists were doing with the Copenhagen interpretation is they thought it had to make sense in classical terms. They were thinking that, well, it seemed to violate logic. Of course, it didn't. You just had to take seriously the idea that reality is multivariate and there's a multiverse. But if you reject that, then you have to try and square what the equations are saying with this multivariate aspect to the formalism with what you think must be going on in reality. You think reality must, in some sense, fundamentally, beneath it all, be classical, single varied. And what Wheeler says about Everett's formulation, he goes on to say, quote, instead of founding quantum mechanics upon classical physics, the relative state formulation uses a completely different kind of model for physics. This new model has a character all of its own. It is conceptually self-contained, defines its own possibilities for interpretation, and does not require for its formulation any reference to classical concepts. It is difficult to make clear how decisively the relative state formulation drops classical concepts. One's initial unhappiness at this step can be matched but few times in history. When Newton described gravity by anything so preposterous as action at a distance, when Maxwell described anything as natural as action at a distance in terms as unnatural as field theory, when Einstein denied a privileged character to any coordinate system, and the whole foundations of physical measurement at first sight seemed to collapse. Okay, I'm going to skip another little bit there and move to where Wheeler says, quote, nothing quite comparable can be cited from the rest of physics except the principle in general relativity that all regular coordinate systems are equally justified. As in general relativity, so in the relative state formulation of quantum mechanics, the analysis of observation is the key to the physical interpretation, end quote. So that is some praise from Wheeler. He's saying that there's only a few times in his great memory of physics and his great understanding of physics where Everett's insight can be matched, and he compares it there to, well, there's no preferred coordinate system in general relativity, whether this observer has this coordinate system and that observer moving at a different velocity has that coordinate system and so on and so forth. And when you get into gravity, the one that is close to the center of the Earth or at the surface of the Earth is different to someone that's far away from the Earth, all that kind of thing. There are different coordinate systems depending upon who's making the observations or measurements in general relativity. That was a huge change compared to Newton, where there was just a fixed single coordinate system for everyone, everywhere, all the time. That is a huge conceptual change. And Wheeler here is saying that Everett is doing the same sort of groundbreaking, revolutionary conceptual move. So far from trying to say, this Everett guy, this junior researcher in my orbit, pay no attention to his nonsense. No, he's giving him not merely praise, but explaining it as clearly as perhaps what Everett could. This is a very, very Popperian way of doing science. Popper would say, try to express the opponent's perspective in as clear a term as possible. These days, people talk about steel manning. Some people say steel manning perhaps goes too far. It's trying to put the perspective of your opponent in terms that they wouldn't, even stronger than what they would put. So perhaps steel manning goes a little bit too far. The Popperian view is try and explain it as clearly as what your opponent would. Give them their due. Don't try to straw man, and perhaps don't even try to steel man. Just state it the way they would, as clearly as what they would. And that's precisely what Wheeler is doing here. Skipping a little, again, well, skipping a lot. And Wheeler goes on to write, quote, in physics, it is not enough for a single observer or apparatus to make measurements. Different pieces of equipment that make the same type of measurement on the same object system must show a pattern of consistency if the concept of measurement is to make sense. Does not such consistency demand the external observation formulation of quantum theory? There, the results of the measurements can be spelled out in classical language. Is not such language a prerequisite for comparing the measurements made by different observing systems? The analysis of multiple observers in the preceding paper by the theory of relative states indicates that the necessary consistency between measurements is already obtained without going to the external observer formulation. To describe this situation, one can use, if he will, the words communication in clear terms always demands classical concepts. However, the kind of physics that goes on does not adjust itself to the available terminology. The terminology has to adjust itself in accordance with the kind of physics that goes on. In brief, the problem of multiple observers solves itself within the theory of relative states, not by adding the conventional theory of measurement to that theory. It would be too much to hope that this brief survey should put the relative state formulation of quantum theory into completely clear focus. One can at any rate end by saying what it does not do. It does not seek to supplant the conventional external observer formulation, but to give a new and independent foundation for that formalism. It does not introduce the idea of a super observer. It rejects that concept from the start. It does not supply a prescription to say what is the correct functional form of the Hamiltonian of any given system. Neither does it supply any prediction as to the functional dependence of the overall state function of the isolated system upon the variables of the system. But neither does the classical universe of Laplace supply any prescription for the original positions and velocities of all the particles whose future behavior Laplace stood ready to predict. In other words, the relative state theory does not pretend to answer all the questions of physics. The concept of relative state does demand a totally new view of the foundational character of physics. No escape seems possible from this relative state formulation if one wants to have a complete mathematical model for the quantum mechanics that is internal to an isolated system. Apart from Everett's concept of relative states, no self-consistent system of ideas is at hand to explain what one shall mean by quantizing a closed system like the universe of general relativity. End quote. What I think after reading that is why wasn't Wheeler convinced? He's convinced me. Why hasn't he convinced himself there? Apart from Everett's concept of relative states, no self-consistent system of ideas is at hand to explain what one shall mean by quantizing a closed system. So, there you go. Powerful words by Wheeler here. And, he's literally saying there that the way to solve this so-called measurement problem is just to assume that you have multiple observers, and the multiple observers are actually observing the same thing. In other words, you have the multiverse. Anyway, it's a brilliant piece. And what it's saying, really, is that Kuhn, we just look at that, that's an example, a perfect refutation of Kuhn. It shows that Kuhn is completely wrong. How can Thomas Kuhn account for something like that? Is it a one-off? I mean, David Deutsch did not have to go searching long for this one. It was well within his wheelhouse. It was just within arm's reach. You can kind of use a reverse Gell-Mann amnesia effect here. Gell-Mann amnesia, that's the idea of you're an expert in a particular field. You'll readily notice that the media, newspapers, television, and social media, I suppose, making mistakes in your area of expertise. Almost as a rule, they get things wrong. Whenever they're doing reports on astronomy, I notice that they make fundamental, simple errors all the time whenever they're reporting on science in general. And whatever your area of expertise is, you watch the news and you find, I've noticed an error there. So the Gell-Mann amnesia effect is that you should conclude that in fields you're not an expert in, then roughly the same thing is going on. The errors being made in fields where you're not an expert by the media are occurring at roughly the same rate as in the fields where you are an expert and you're noticing them. So to bring it back to this situation here, in this case, given David could find, within arm's reach, an example of this supposed, in rough Kuhnian terms, and the way David explains it, we've got this exemplar, Wheeler, the supposed old fogey, but he wasn't stymieing the young upstart Everett. Instead, he was helping him. He was helping him get the ideas out there. And it's almost as if Wheeler was persuaded. Now, he wasn't, but the way he writes there, you can well understand why people at the time called it the, Wheeler-Everett or the Everett-Wheeler theory of quantum theory. So you can imagine, going to the reverse Gell-Mann effect, that in areas where David Deutsch is not an expert, precisely the same thing is going on, where these supposed old fogies are actually not stymieing the young upstarts, they're helping them. And in fact, that is true. That is what goes on. Not always, but the fact that it does happen is crucial. Both can happen simultaneously, perhaps. Perhaps some scientists try to thwart others they disagree with. But perhaps at the same rate, or at a slightly faster rate, scientists help each other, even when they disagree. The point is, Kuhn's account cannot possibly be a universal one, because it doesn't work in all cases. As David goes on to write, quote, Wheeler's exemplary adherence to scientific rationality may be extreme, but it's by no means unique. In this regard, I must mention Bryce DeWitt, another eminent physicist who initially opposed Everett, end quote. Just recall that Bryce DeWitt was a colleague of David at one time, or supervisor, indeed boss, I think David has referred to him as. We might call DeWitt the bridge between Everett and Deutsch. DeWitt really promoted Everett in quantum theory early on. He persuaded Deutsch of the truth of the multiverse. And so we've got that lineage, really, of promoting that particular explanation and indeed building on it, that, the explanation that is the multiverse, the relative state formulation, however you want to put this, Everettian quantum theory, going from Everett to DeWitt to Deutsch, and now Deutsch's many associates, colleagues, I wouldn't call them students, but people who work with Deutsch, like Sam Kuipers and Maria Villaris and so on and so forth. David goes on to say, quote, in a historic exchange of letters, DeWitt put forward a series of detailed technical objections to Everett's theory, each of which Everett rebutted. DeWitt ended his argument on an informal note, pointing out that he just couldn't feel himself split into multiple distinct copies every time a decision was made. Everett's reply echoed the dispute between Galileo and the Inquisition. Do you feel the Earth move? He asked. The point being that quantum theory explains why one does not feel such splits, just as Galileo's theory of inertia explains why one does not feel the Earth move. DeWitt conceded, end quote. So there you have it. Criticism back and forth before DeWitt adopted the multiverse interpretation, just as it should be. But it wasn't like there was appeals to authority. There was just criticism backwards and forwards until one person conceded that the other person had convinced them and that there was only one good explanation remaining. And that back and forth was, therefore, it happened regardless. The persuasion of DeWitt by Everett happened regardless of any social or emotional factors. David goes on, quote, nevertheless, Everett's discovery did not gain broad acceptance. Unfortunately, in the generation between the Copenhagen interpretation and Everett, most physicists had given up on the idea of explanation in quantum theory. As I said, it was the heyday of positivism in the philosophy of science. Rejection or incomprehension of the Copenhagen interpretation, coupled with what might be called pragmatic instrumentalism, became and remains the typical physicist's attitude to the deepest known theory of reality. If instrumentalism is the doctrine that explanations are pointless because a theory is only an instrument for making predictions, pragmatic instrumentalism is the practice of using scientific theories without knowing or caring what they mean, end quote. I always want to say at this point, when we get into discussions about instrumentalism in particular, that this issue really only arises in physics, and even there, only in fundamental physics, and in particular, quantum theory, perhaps relativity, sometimes historically speaking. But anywhere else in science, in geology, for example, the rocks are real. They exist, and their properties are explained in terms of how they are formed, whether by sedimentation in rivers or solidification of lava from volcanoes for igneous rocks, or by pressure and temperature on both of those to form metamorphic rocks. These are explanations in geology. And in fact, You go far enough in geology and you end up unifying everything from the structure of the Earth itself as the mantle and volcanoes and erosion and other things, and they're united in turn with geophysics and how we know the full structure of the Earth given seismology and refraction and reflection techniques. It's not just about trying to predict, the formation of rocks. It's explaining what exists and how it arose in terms of really existing things. The same as in chemistry. We don't just have instrumentalism. We say why an acid is an acid and how neutralization with a base actually occurs in terms of molecules of hydronium ions and hydroxide ions and so on. And in biology, we're also not trying to predict instrumentally using neo-Darwinism. It's not an instrument for prediction. We're explaining the diversity of really existing creatures, living things, organisms. So anyways, all these versions of instrumentalism, they're kind of very, very parochial philosophies. They're not universal. They apply to aspects of physics, fundamental physics, ignoring most of science and most of the rest of the intellectual endeavors of human beings. And that should be a huge red flag for philosophers, and philosophers of science in particular, and physicists who attempt to adopt instrumentalism. Let's keep going with David. He writes, quote, "In this respect, Kuhnian pessimism about scientific rationality was borne out. But the Kuhnian story of how new paradigms replace old ones was not borne out at all. In a sense, pragmatic instrumentalism itself became a paradigm, which physicists adopted to replace the classical idea of an objective reality. But this is not the sort of paradigm that one understands the world through. In any case, whatever else physicists were doing, they were not viewing the world through the paradigm of classical physics, the epitome, among other things, of objective realism and determinism. Most of them dropped it, classical physics, most of them dropped it almost as soon as quantum theory was proposed, even though it had held sway over the whole of science, unchallenged, ever since Galileo won the intellectual argument against the Inquisition a third of a millennium earlier." End quote. So the point there is that Kuhn cannot account for the fact that if some scientists are wedded to existing theories because they cannot think outside their own paradigms, which blind them literally to new ideas, then how on earth do we explain how physicists dropped classical physics for quantum physics so quickly? Now, when we say quantum physics here, we're not talking about the Everettian relative state formulation. We're not saying they endorsed the multiverse, but they did drop classical physics. They went, that doesn't work anymore. They admitted, they conceded, they recognized that quantum physics solved a bunch of problems in physics that classical physics could not. The so-called ultraviolet catastrophe. This was the prediction, given existing classical physics, that if one heated something up, this is known as the ideal black body, that's what it's called in physics, you heat up this black body, what should happen is that the energy radiated would go to infinity. But that's not what happens. What we get instead is the so-called characteristic black body radiation curve. Incidentally, that curve is close to, but not identical to, the curve of energy produced by a star. In any case, the solution, why you get one curve in reality explained by and predicted by quantum physics, but predicted quite differently by classical physics, the solution is that the energy radiated is not waves, it's discrete chunks, particles known as photons. And my favourite, as many of you know who've perhaps listened long enough to Talkcast, is the photoelectric effect. This cannot be explained by classical physics. The idea here is that, well, according to classical theory, the classical theory of electromagnetism, then energy can be gradually absorbed by, let's say, atoms, or electrons more precisely. Electrons can gradually absorb energy as light is shone upon them, and no matter how low the energy of the radiation. So, for example, if you have very low red light, for example, just shine it for long enough and the atom will absorb enough energy such that you will get emission or ionization of the atom, emission of electrons, roughly speaking. But it's just not true. That's not what happens. The effect is not gradual. It's instant, but only if the chosen wavelength of light, energy of photon, is sufficient, if you're above the threshold frequency, so-called. It doesn't happen otherwise. You can shine red light all day long onto metals, for example, that do emit electrons, and it doesn't matter for how long you're allowing this metal to absorb the energy, no electrons come off it. But if you choose, ultraviolet radiation or blue light or something like that, then instantly the electrons come off. Can't be explained by classical theory, can be explained by quantum theory. All these experiments, and there are many, many more, those various experiments are problems when considered in the light of classical physics, but they are solved by quantum physics. And scientists, physicists, like nice, clean solutions like that, and so they all adopted, almost all, adopted that quantum way of thinking. Now, not all of it, not wholesale, and of course, yes, with lots of confusion about what was going on, but they could recognize that classical physics wasn't the answer. They weren't, as a group, all resistant to these new ideas about quantization, photons, and entanglement eventually, and so on. They weren't resistant to these ideas because they were trapped in some old paradigm. That isn't the history. The history simply is that by around about 1925 through to 1927, which is barely a few years, or at most a couple of decades after all of these problems began to arise, almost all physicists admitted that, one, quantum theory explained everything classical theory failed at with respect to those experiments. Quantum theory, two, quantum theory made precise testable predictions, and three, it was actually able to unify radiation, matter, chemistry, spectroscopy, among other things. Paul Dirac, the famous quantum physicist, said, quote, "The fundamental laws necessary for the mathematical treatment of a large part of physics and the whole of chemistry are thus completely known," end quote. This is a nice summary of the state of the physics community. They really did move almost entirely wholesale from regarding classical physics as basically the final word towards the end of the 1800s to the notion that quantum theory was the best and indeed only explanation of many things by the beginning of the 1900s. That is a complete refutation of Kuhn. Again. So let's keep going. And David writes, quote, "Pragmatic instrumentalism has been feasible only because in most branches of physics, quantum theory is not applied in its explanatory capacity. It is used only indirectly in the testing of other theories, and only its predictions are needed. Thus, generations of physicists have found it sufficient to regard interference processes, such as those that take place for 1,000 trillionth of a second when two elementary particles collide, as a black box. They prepare an input, and they observe an output. They use the equations of quantum theory to predict the one from the other. But they neither know nor care how the output comes about as a result of the input. However, there are two branches of physics where this attitude is impossible, because the internal workings of the quantum mechanical object constitute the entire subject matter of that branch. Those branches are the quantum theory of computation and quantum cosmology, the quantum theory of reality as a whole. After all, it would be a poor theory of computation that never addressed issues of how the output is obtained from the input. And as for quantum cosmology, we can neither prepare an input at the beginning of the multiverse nor measure an output at the end. Its internal workings are all there is. For this reason, quantum theory is used in its full multiverse form by the overwhelming majority of researchers in these two fields," end quote. So, here with quantum computation, as we've been over many times on my podcast here, see these episodes, for example, that break down quantum computation. We can ask the question, as many people have, if you're trying to understand how quantum computation, quantum computers, would achieve the feats they are capable of achieving, Where is the computation being done? If solving some problem, in particular some mathematical problem, would take more time than exists in the universe and more computational power than can be harnessed by using all the matter in the universe, how is the computation performed? It can't be by recourse to a single universe. If it is performed, therefore, we can only appeal to material outside of our universe, namely in the multiverse. We harness other really existing universes. So that's one thing if you want to explain how quantum computers can possibly work. And quantum cosmology, well, here, if in other so-called interpretations of quantum theory, special physics is required for observers to collapse wave functions or whatever else, we have a problem at the beginning of time, or at any other time, really, because there is no external observer. With Everettian quantum theory, again, this issue dissolves into a pseudo-problem because all physically possible paths are taken by particles in the universe. And on the cosmological scale, we can say that there is no moment in time where there is a single t equals zero. There's no beginning to time on this account where creation happens at that instant. There's no unique initial moment. For what it's worth, if you study cosmology, astrophysics, you hear about the Hartle-Hawking picture of cosmology by those two great physicists, Stephen Hawking. It's like this as well. Their idea is now interpreted as a multiple histories one, which Everettians would say is a multi-universe one, of course. Those histories that Stephen Hawking talks about in his cosmology, in order to explain what the universe looks like now, those histories are real. They also imply not only multiple histories, but the multiple histories imply multiple presents and therefore multiple futures, a multiverse. And also the initial conditions of the universe, on this account, were not just one single state according to quantum cosmology. Okay, quantum theory as applied to the universe as a whole. There must have been an ensemble of states that evolved independently at the beginning of everything. So in quantum computation and quantum cosmology, the multiverse is absolutely central to understanding what is actually going on. Now, David continues, quote, "So Everett's story is indeed that of an innovative young researcher, challenging a prevailing consensus and being largely ignored until decades later, his view gradually becomes the new consensus," end quote. We should emphasize, at least in those fields. David goes on, quote, "But the basis of Everett's innovation was not a claim that the prevailing theory is false, but that it is true," end quote. Precisely as Wheeler said in the parts of the paper that I just read out. David goes on, quote, "The incumbents, far from being able to think only in terms of their own theory, were refusing to think in its terms and were using it only instrumentally. Yet they had dropped the previous explanatory paradigm, classical physics, with scarcely a complaint as soon as a better theory was available. Something of the same strange phenomenon has also occurred in the other three theories that provide the main strands of explanation of the fabric of reality, the theories of computation, evolution, and knowledge. In all cases, the theory that now prevails, though it has definitely displaced its predecessor and other rivals in the sense that it is being applied routinely in pragmatic ways, has nevertheless failed to become the new paradigm. That is, it has not been taken on board as a fundamental explanation of reality by those who work in the field. The Turing principle, for instance, has hardly ever been seriously doubted as a pragmatic truth, at least in its weak forms. For example, that a universal computer could render any physically possible environment. Roger Penrose's criticisms are a rare exception, for he understands that contradicting the Turing principle involves contemplating radically new theories in both physics and epistemology, and some interesting new assumptions about biology too. Neither Penrose nor anyone else has yet actually proposed any viable rival to the Turing principle, so it remains the prevailing fundamental theory of computation. Yet the proposition that artificial intelligence, just a footnote here, I'm going to insert the word general because when David mentions artificial intelligence in the fabric of reality, and even in the beginning of infinity, that was the old terminology before artificial intelligence, that term, got completely denuded of its original meaning. So I'm going to I rarely do this, subtly change the way it appears here. So for every instance of artificial intelligence that David writes here, I'm going to insert general. So let me begin that again. Yet the proposition that artificial general intelligence is possible in principle, which follows by simple logic from this prevailing theory, is by no means taken for granted. An artificial general intelligence is a computer program that possesses properties of the human mind, including intelligence, consciousness, free will, and emotions, but runs on hardware other than the human brain. The possibility of artificial general intelligence is bitterly contested by eminent philosophers, including Alas Popper, scientists and mathematicians, and by at least one prominent computer scientist. But few of these opponents seem to understand that they are contradicting the acknowledged fundamental principle of a fundamental discipline. They contemplate no alternative foundations for the discipline, as Penrose does. It is as if they were denying the possibility that we could travel to Mars without noticing that our best theories of engineering and physics say that we can. Thus, they violate a basic tenet of rationality, that good explanations are not to be discarded lightly, but it is not only the opponents of artificial general intelligence who have failed to incorporate the Turing principle into their paradigm. End quote. The wonderful thing there is that we see this is the end of the fabric of reality, and we can see a highway leading straight to the beginning of infinity. Because we're talking about there, basically, that if it's not prohibited by the laws of physics, then it's possible. If the laws of physics are that, well, you can travel as far as you like, as fast as you like, up to the speed of light, then you can get to Mars. Obviously, no one rejects the idea that we could get to Mars if only we could solve the engineering problem. But on the other hand, when it comes to artificial general intelligence, the possibility of AGI, the only thing that's stopping us is not any law of physics, despite what people like Penrose might say, because our best understanding of physics right now is that the Turing principle is a genuine principle of physics that applies always, everywhere, to any physical system. And so if it can be done in physical reality, such as what our brains are doing right now, then it can be done by a computer as well, because the computer can simulate the thing. And what we're talking about here is computations. And so if the computations could be done here, they can be done inside of a silicon computer as well. And all of what David is saying there is basically my experience in having tried to explain this over the last few years. But it's almost the reverse, actually. There are some people, but I encounter these more and more rarely, the people who say AGI is not possible at all. There are some out there, but, I spend time on X where a lot of the tech people are, and there are some scientists there as well, and I don't hear them rejecting the possibility of AGI, yet this is what David is talking about. These days, I think what is more common among so-called rationalists and people in science and tech, they accept there's no additional magic fairy dust in human brains that give rise to consciousness. They understand that grey matter obeys the same laws of physics as everything else. In fact, I even had this discussion with both Michael Shermer and Brett Weinstein, and although initially they were sort of both of them, I kind of got the impression, especially from what I had heard them say elsewhere on their own podcasts and things, that they thought there was some kind of magic fairy dust when it comes to consciousness. Everyone always wants to talk about consciousness as if it's magical. It's just an open problem. I don't think we need to change the laws of physics for it. But in a conversation with them, like with everyone else that I talk to about this that has some sort of interest in AI, AGI, consciousness, that kind of thing, pushed enough, or just have a discussion with them for long enough, if they're a rational person and they're willing to take seriously the scientific worldview, they concede, okay, whatever's going on inside of our brains has to just be obeying the laws of physics. It's either that or magic. So if our best laws of physics include the Turing principle, which is every physical process can be simulated by a computer, then therefore computers can be conscious as well. And people are usually convinced by that these days. As far as I can tell, there are some other people who I haven't spoken to who might reject that. They're religious people, but I usually don't get into discussions with them about this sort of thing. In any case, nevertheless, the Turing principle still, for other reasons, I would say, is not taken seriously enough. So I will end up in debates with people who want to argue there is super intelligence, the thing that can fly free of known physics, including the Turing principle, and therefore can compute things that we, AGI, cannot possibly ever do. These opponents of the Turing principle, at least implicitly, the believers in superintelligence, they assume there exists a kind of supercomputation. They never explain what it is or suggest how it might work. They just think that you reach a kind of phase change at some point where you're getting this exponential increase in intelligence until you achieve a new kind of escape velocity to something supernatural. And as I have said in videos and various other places, it genuinely is just an appeal to the supernatural. I'm not going to go into all of that again. You can look up my many recent podcasts all about this. Anyways, David goes on, and I'll just repeat the last part that I said and continue. Quote, "But it is not only the opponents of artificial general intelligence who have failed to incorporate the Turing principle into their paradigm. Very few others have done so either. The fact that 4 decades passed after the principle was proposed before anyone investigated its implications for physics, and a further decade passed before quantum computation was discovered, bears witness to this. People were accepting and using the principle pragmatically within computer science, but it was not integrated with their overall worldview. Popper's epistemology has, in every pragmatic sense, become the prevailing theory of the nature and growth of scientific knowledge. When it comes to the rules for experiments in any field to be accepted as scientific evidence by theoreticians in that field, or by respectable journals for publication, or by physicians for choosing between rival medical treatments, the modern watchwords are just as Popper would have them: experimental testing, exposure to criticism, theoretical explanation, and the acknowledgement of fallibility in experimental procedures. In popular accounts of science, scientific theories tend to be presented more as bold conjectures than as inferences drawn from accumulated data. And the difference between science and, say, astrology is correctly explained in terms of testability rather than degree of confirmation." End quote. An absolutely crucial point there. After all pseudoscience, including astrology, could otherwise be justified on the basis that some evidence has accumulated in its favour at some time. Sometimes in some places, astrologers might seem to get a prediction right, and so that would seem to be evidence accumulating. Or some aromatherapy or homeopathic nostrum actually appears to cure someone's illness. Basically, the actual reason is because they get better, because their own immune system kicks in for reasons we don't fully understand. Their immune system cures them, but they attribute the cure to taking the nostrum. The point is that the claim, astrology or homeopathy works because it apparently did in this instance, and then this instance and this instance, so on and so forth. That claim, that so-called accumulation of evidence of it apparently working, cannot possibly be distinguished from coincidence if all you are ever doing is looking at correlations between engaging in this practice and this other thing happening. The better standard is, what is the cause of the effect, and can it be reliably tested? And even more than this, in explicitly modern epistemological terms, what is the explanation of how it works that is consistent with the laws of physics and so on? Let's keep going. David goes on to say, quote, "In school laboratories, hypothesis formation and testing are the order of the day. No longer are students expected to learn by experiment in the sense that I and my contemporaries were. That is, we were given some equipment and told what to do with it, but we were not told the theory that the results were supposed to conform to. It was hoped we would induce it. Despite being the prevailing theory in that sense, Popperian epistemology forms part of the worldview of very few people. The popularity of Kuhn's theory of the succession of paradigms is one illustration of this. More seriously, very few philosophers agree with Popper's claim that there is no longer a problem of induction, because we do not in fact obtain or justify theories from observations, but proceed by explanatory conjectures and refutations instead. It is not that many philosophers are inductivists, or have much disagreement with Popper's description and prescription of scientific method, or believe that scientific theories are actually unsound because of their conjectural status. It is that they do not accept Popper's explanation of how it all works. Here again is an echo of the Everett story. The majority view is that there is a fundamental philosophical problem with the Popperian methodology, even though science, wherever it was successful, has always followed it. Popper's heretical innovation takes the form of a claim that the methodology has been valid all along, end quote. And that's where I'll end the reading, but not the commentary for today. So there, David says that Popper is being both descriptive and prescriptive. So he's saying how science works and how it should be done. And Popper is genuinely saying, look, this is simply how science works, past, present, and future. It's like discovering, this idea of conjecture and refutation, Popperian epistemology, saying that it applies to how science has worked, is working, and must always work. It is precisely the same kind of discovery that Einstein made about what gravity is and how orbits truly work. Einstein explained that, and Popper explained how scientific theories themselves come to be the prevailing view in their discipline and how they're replaced by better theories over time. Both inside science and outside, we should also note, it also accounts for how history makes progress. And indeed, you could talk about morality and politics and art, anything you like. It's about guessing and then criticizing those guesses. That's the fundamental idea. Now, as to Everett and what has happened in quantum physics, again, physicists working within the classical framework in like the sort of the interwar period, if you like, between about 1920, 1930, they moved rapidly to adopt quantum theory. Yes, with some confusion and with an application of silly instrumentalism, later on. But adopt it they did, even if incorrectly. And Everett's experience within the community of physicists was that his theory was pushed forward by an opponent of it, Wheeler, precisely so that the engine of criticism and correction, that is science, would be applied to it. Why was Wheeler doing that? He wanted to not only promote a colleague of his in the work, but he saw value in the idea, let's lift this thing up so that if it truly isn't correct as I think it is, it will be shot down by valid critiques and a better idea offered for understanding this quantum theory thing. Now, of course, the fact that Everett's explanation has not been well understood is not his fault, and nor is it the fault of science. So what is the cause? Well, it is the fault of bad philosophy, as David says. He fleshes this out in the beginning of Infinity, of course. And that is not much at all of a sociological phenomenon. It is not about physicists in their various tribes pitching tents and refusing to move. The explanation, as David gives in the beginning of Infinity, is them individually each coming to have a bad philosophy operating on their minds when they reject explanation in favor of instrumentalism. That's the bad philosophical move. And that idea that right here in quantum theory, no explanation is needed, we just need to predict, it's a kind of anti-rational meme. Because if one takes it seriously, if one takes seriously the idea that, well, explanation is not important, then one cannot be readily argued out of that position by explanation. After all, explanation is the very thing that's being rejected by the instrumentalist. On this point, Deutsch has an accurate account of why Everett was not as successful as, say, Darwin was in persuading others of the truth of his own revolutionary idea. So far. It's not because of social factors, but philosophical ones. And so Popper is correct, therefore, about how science itself self-corrects and makes progress through conjecture and refutation. And that happens through experiment and argument. Kuhn is quite clearly wrong. Either social factors are the main driver of scientific discovery or they're not. Now, Popper does not deny social factors. He doesn't say there's no place for social factors whatsoever. I provided quotes earlier on. But it's not like Popper's endorsing some version of Kuhn. And some people get this thing wrong. And they say to me, well, they want to be centrists on this point. They say, well, Popper is right about falsification. However, there are also these important social factors to take into account. No, they're not important to the process of science. You can't mix a little bit of poison in with your food and say you've somehow improved things because, hey, food is good sometimes, but maybe a little bit of poison will help as well. No, Kuhn is the poison in this sense. Okay, it might be a bit harsh, but the Kuhnian idea that social factors play the central role in transitioning from one scientific theory to the other is simply false. Popper denies that, but he doesn't say they have no role. He doesn't say they have no role. He admits emotion and social factors do something. They have some effect. It is, therefore, eminently Popperian to say social factors affect scientists like anyone else. But Popper is saying, however, that the nuts and bolts of science are like the literal nuts and bolts of wings and engines on an aircraft. It's not social factors that keep the aircraft flying, even if, quite clearly, it is important that pilots get along, for example, while they fly an aircraft, and that they understand each other. Indeed, mishaps, disasters on airline passenger craft have happened because of social factors, miscommunication or poor communication between pilots in the cockpit. We can concede that. The deeper point is, if you're a scientist, a physicist, an aircraft engineer, even a pilot, if you, or a prospective pilot, let's say, if you demand an explanation of how heavier than air flight works, in other words, how a jet flies, you're not asking about what pilots get up to inside cockpits. That's a detail that comes later and after you actually get the explanation of flight. The explanation involves, well, 4 basic things. We can start this way: thrust, drag, weight, and lift. And those 4 forces can be then further broken down. But that's your basic explanation. It comes down to thrust causing lift, and the lift is due to angle of attack and Bernoulli's effect and so on. Differential pressure on either side of the wing. We're not seeking. But what about how engineers got along in the design room in shaping the wing? And what about how pilots communicate? And what about if a terrorist brings a bomb on board? Don't those things also affect the ability of a plane to fly? Of course they do. But that's a silly, misdirected question that's not actually answering the question that was asked. How do jets fly? Saying that, well, they can be blown out of the sky by a bomb isn't answering the question. In the same way, yes, can science go off track if there is a community of scientists who are all captured by a bad philosophy? Yes, but that's not how science works. So in the same way, I would argue, asking about, but what effect to scientists and social factors and scientists being stuck in their paradigms have on the process of science is like asking all of that stuff about social factors with respect to how jets fly. It's missing the point. And the point of conjecture and refutation is everything. That's your thrust and lift. That's the whole exercise to a first approximation. Aerodynamic shape of the wing and the elevators and the rudders and the flaps, well, there's your experimental testing and your good explanation and your repeatability, if you like. And we could go on. And way down on the list, once an engineer, an aeronautical engineer in particular, understands all of that, then maybe they can also make a note about how to make the cabin and the cockpit just the right shape and level of comfort to help ensure all the rest goes smoothly. But cockpit designs, which take into account social factors, are not where the discussion begins or ends. It's where a footnote appears in the texts on, let's say, the principles of aerodynamics or in the philosophy of science, respectively. Thomas Kuhn is literally the sociologist in all this, with respect to keeping aircraft aloft, or explaining how the jet of scientific progress remains aloft and speeding forwards. But Popper's like the aeronautical engineer. He's not saying terrorists can't cause planes to fall from the sky, nor that pilots sometimes cannot make bad moves, causing an aerodynamic stall at times. He's not denying any of that. He's just giving an account at the right level of how this magnificent machine that is science actually flies. Okay, so I hope you got something out of all that. If you'd like to support this endeavour, as always, my Patreon is available. Next time we'll be going into computation in more detail with some remarks from the Fabric of Reality about how even human values can be incorporated into this worldview. Until then, bye-bye.